Hello everyone, my name is Nicholas Theodoropoulos. I am the R&D manager at Advent Technologies. Thank you for joining this training session. Today I will give you a brief introduction to who we are, what we do, and then we will dive into the core topic of this session, the membrane electroassembly, or the MEA. Advent Technologies is a global company working at the forefront of fuel cell innovation. We specialize in hydrogen and methanol technologies with a strong focus on developing the most critical components of fuel cell systems, namely membranes, the membrane electroassembly, and the fuel cell stack. Our headquarters are located in Livermore in California. In Europe, we have offices in Athens, Kozani, and Patras in Greece. Our R&D and MEA manufacturing departments are based in Patras, where a lot of innovation happens. This video will focus on the membrane electroassembly. The membrane electroassembly is a key component of the fuel cell system. It's where electrochemical reactions take place, and it plays a major role in determining the performance, efficiency, and durability of the entire system. Let's start with the fundamentals. Fuel cells generate electricity through an electrochemical process similar to how battery works, but with a key difference. Instead of storing energy internally, fuel cells rely on a continuous supply of fuel from the outside. In typical fuel cell, hydrogen reacts with oxygen in a controlled environment. This reaction produces electricity along with water and heat as byproducts. It's a clean and efficient process, and it's what makes fuel cells so promising for the future of energy. Unlike batteries, which eventually run out of charge, fuel cells keep working as long as they are fed with fuel. Common fuels, hydrogen, methanol, and even natural gas. This makes them highly adaptable for different applications, from portable devices to large-scale power systems. A single fuel cell produces a small amount of power. To generate more electricity, we combine multiple cells into what is called a fuel cell stack. Each cell adds to the total voltage and power output, and the stack can be scaled up or down depending on the energy needs of the application. Before I jump in, I know there is a wide range of people on this training, and I will start with some basics. I assume that if you know these basics, you will be able to go deeper and identify all the individual parts of an MEA. You hear a lot of us discuss membrane electroassemblies or MEAs, and in the simplest of descriptions, it consists of membrane in the middle, like a sandwich. On either side of it, you have what we call gas diffusion electrodes. These are composites made of catalyst-coated carbon, cloth, or carbon paper. You have an anode, you have cathode, and basically the anode is fed with hydrogen, while cathode is fed with air. The hydrogen gets oxidized, releasing protons and electrons. The protons pass through the membrane to the cathode side. On the cathode we feed in air, specifically the oxygen in the air. The oxygen gets reduced, and when it meets the protons, they form water. All this you can see in this picture of the side, where we have the inertial gasket, we have the gas diffusion electrode, the catalyst, and the membrane. And that really is the basis of our technology. Once you have the MEA, the next step is assembling it into a fuel cell stack. A fuel cell stack is made up of several layers, including the bipolar plates, which serve as flow fields of hydrogen and air, the end plates, which provide structural support and allow the stack to be compressed tightly. And almost like a battery, you have many of these plates, and if you need to go to a higher voltage, you have more plates. If you need to go to a higher current, you have bigger plates. And this is really the second part of the technology. But the key part is the MEA. It's the MEA that defines the performance, the efficiency and durability of the entire system. Now, when you think about the world of MEAs, there is some very stiff competition out there. There are many players in the field, each pushing the limits of performance, cost and scalability. That's why our work in R&D is so critical. To stay ahead, we need to keep innovating. Let's start first with the first PEM MEAs, which was the low temperature proton exchange membrane MEAs. Take a little bit about the history. The first membrane patent from DuPont for what's called NICKEFFECT back to 1966. That's ancient. It was actually General Electric that developed what they called the SPE solid polymer electrolyte fuel cell as an alternate to what then was alkaline liquid fuel cells that came about in the 70s. Then it really was not until the 90s when the scientists at Los Alamos really pioneered very advanced MEAs, low precious metal, very high current using the basic DuPont NICKEFFECT membrane for low temperature. What you should realize is that billions, tens of billions, and actually upper tens of billions of government and private funds have gone into developing the low temperature PEM. So, in a way, you can think of it as stiff competition. If you compare what we can do today with our current materials to low temperature PEM, there are really some key metrics that are being exceeded by low temperature PEM that we, with our current product, have not been able to attain. And that is, number one, far higher peak power, and probably this is the biggest difference. Number two, through these years of development and funding, lower platinum usage because it can start at lower temperature, very fast startup time, and typically longer lifetimes. Part of that has to do with the MEA, but part of that also has to do with just the many years of developing systems and understanding what components are being failed. But again, you should remember low temperature PEM is an old technology. In fact, I pulled off the Gore website. It was 1994 that they started to develop their membranes for low temperature PEM. Also, 3M spent more than 20 years in developing the technology. So this is really old style technology, which is, in a way, has really picked out on how much more it can be improved. They are sort of at the end of their development cycle. So for us, I would like you to step back and think if we had new materials that were higher performing, what would be possible? Let me just try to imagine what if we had a MEA with 5 times the lifetime that we currently have. What if we had an off-grid generator set that actually beat diesel on both OPEX and CAPEX? What about if we had a high temperature PEM MEA with the power of a low temperature PEM? If we did, we could have transportation power systems that actually would beat today's fuel cell leaders, and we could have leaders in ground and air transportation. We also would have an HT-PEM stack with outstanding heat control that really would beat the low temperature PEM. Also, we would have stationary power systems that would challenge solid oxide multicarbonate fuel cells and phosphoric acid fuel cells. And we do have that material. That material is called ion pair. It was developed by Los Alamos National Laboratory. They have been working on it for close to a decade, but intensively over the last 5 years. This new material offers 2 times more power, 5 times more lifetime. We expect this technology to be an industry game changer, enabling fuel cells to be deployed with the current fuel availability and resilience issues. Advent owns unique IP on the core technology and the manufacturing scale-up of this MEA. Let's talk now about the size of the MEAs. MEAs are essential to the fuel cell performance, and their size can vary depending on the design and the purpose of the fuel cell stack. The size directly impacts the power output, the efficiency, and application of the system. There are several standard sizes commonly used in fuel cell stack industry. Starting from the 5 square centimeters, which is suitable for small-scale applications or testing. We have the 25 square centimeter MEA, common in medium-sized fuel cells, the 45 square centimeters, which provides a balance between size and power output, the 165 square centimeters that used in large fuel cell stacks for higher power outputs, and 605 square centimeters, which is ideal for large-scale applications with significant power needs. Of course, MEAs can also be customized to meet specific needs, and Advent can provide these MEAs. Custom sizes allows us to optimize performance for unique fuel cell configurations and specialized applications. This flexibility is one of the strengths of our technology, and Advent can cover this. So the question really is, what is an ion pair? To answer that, let's first look at what we are using today. Currently, many high-temperature PEM systems uses PBI, a type of engineering polymer. PBI is a film that absorbs phosphoric acid, but it really absorbs it like a sponge. So it does not really have a high affinity for the phosphonate. In fact, you can squeeze it out. Advent's R&D has put a lot of time into understanding just how much to squeeze these materials so you don't destroy them. On the other hand, ion pair is more of a concept. It's not a thing. It's a membrane that forms a film, and you actually make an insoluble salt between positively charged membrane and phosphoric acid, and the salt binds tightly. In fact, it actually binds 10 times stronger than the PBI does. This is what allows us to work at higher temperatures, higher powers, and be more stable. But there is a second part to the story of ion pair. Not only it is a film, but it's an electrode technology. So there are two technologies wrapped into one. The electrode for PBI today, because of this relatively liquid phosphate, has to be thick, and it contains Teflon to guarantee that the acid does not come out of the electrode. This is one of the reasons why we can operate or only operate at low currents for the PBI product. On the other hand, the ion pair electrode has a special ionomer binder, not PTFE, but something that's a lot more closer to binders used in low temperature PEM technology. Thus, we can make very thin layers of the electrode, and that's really what allows us to support high current operations. Again, closer to low temperature PEM architecture with the ability to run at higher temperatures. Lastly, the manufacturing of the ion pair electrodes should actually be lower cost processed than the current PBI electrodes. Now, let's take a closer look at how we actually manufacture the membrane, one of the most critical components in our fuel cell technology. The process begins with monomers, which are basic building blocks. These monomers go through a polymerization process to form long-chain polymers. Once we have the polymer, we process it into a fine bounder. This bounder is then fed into a casting machine, where it's formed into a thin film. This is the early stage of the membrane. From there, The film undergoes further processing to become the final membrane product, ready for integration into the MEA. When we design and manufacture a membrane, there are several essential properties we need to get right. The membrane should exhibit high proton conductivity to facilitate the transport of protons from the anode to the cathode. It needs to remain stable under the fuel cell's operating conditions, temperature, humidity, and chemical exposure over long periods. A thinner membrane improves proton transport but may be fragile. A thicker one is stronger but can reduce conductivity. So we aim for the right balance. We want to minimize the leakage of hydrogen or oxygen through the membrane. High crossover reduces efficiency and can pose safety risks. The membrane's resistance adds to the total internal resistance of the fuel cell. Lower resistance means better efficiency. The membrane should have adequate mechanical strength to withstand the operating conditions including temperature, pressure, and humidity fluctuation. It should resist mechanical deformation and maintain its integrity over the lifetime of the fuel cell. Finally, the cost is an important parameter for commercial viability. The membrane material and manufacturing process should be cost-effective to ensure widespread adoption of PEM fuel cell technology. Let's now walk through the manufacturing process of the gas diffusion electrode or GDE, an essential part of the membrane electrode assembly. The process begins with the preparation of a conductive support. This is typically a carbon cloth, carbon paper, or metal mesh. We refer to this as the web and it forms the foundation of the electrode. Next, we apply hydrophobic wet-proofing layers to the web. These layers are critical. They help manage the delicate balance between gas and liquid inside the electrode, ensuring that gases can diffuse properly while preventing flooding. Then we apply a catalytic layer to one side of the web. This layer usually contains precious metal particles like platinum mixed with a binder. This layer enables the electrochemical reactions that power the fuel cell. After the layers are applied, the electrode goes through a sintering process. This step helps bond the materials together, improving durability and performance. Finally, the finished GDE undergoes rigorous quality control. We test for things like pore size distribution, electrical conductivity, catalytic activity. This ensures every electrode meets our standards for performance and reliability. In the slide below, you can also see the internal structure of the GDE. The membrane in the center, a microporous layer, and a PTFE-bound carbon particle layer which enhances gas diffusion and water management. Here you can see two types of gas diffusion layers or GDL that serve as the foundation for the electrode, carbon paper and carbon cloth. On the left we have a semi-image of carbon paper. This material is made from carbon fibers bonded together in a paper structure. It offers good electrical conductivity, excellent gas permeability, and effective water management. Carbon paper is also mechanically robust, which makes it a popular choice in PEM fuel cells. On the right, we see carbon cloth shown both in a semi-image and as a physical sample. Carbon cloth is made from woven or knitted carbon fibers, giving high electrical conductivity, strong gas permeability, and good mechanical strength. It is well suited for a variety of operating conditions and is often used where flexibility and durability are needed. Another critical part of the membrane electroassembly that drives the core electrochemical reactions in a fuel cell is the catalyst layer. It is typically made of a porous mixture of carbon-supported platinum and ionomer. For the catalyst to work effectively, it must be in contact with both protonic and electronic conductors. This ensures that the reactions can happen efficiently. The catalyst layer plays a central role in the fuel cell's operation. At the anode, it helps split hydrogen molecules into protons and electrons. At the cathode, it enables oxygen to combine with those protons to form water. These reactions are what generate electricity in the fuel cell. The catalyst layer is incredibly thin, usually between 5 and 30 microns. Despite its size, it has a complex internal structure with multiple phases, porosity, and active reaction zones. When we look at it under a scanning electron microscope, we see an agglomerate-type structure. The electrocatalyst is supported on carbon agglomerates, and it's covered by a thin layer of membrane that helps manage proton transport. The catalyst layer starts with a carefully formulated ink. This ink typically includes platinum carbon as the active catalyst, carbon black to ensure conductivity, PTFE to provide hydrophobicity and structural support, and a mix of solvents and surfactants to ensure proper dispersion. This ink is then sprayed or printed onto a carbon paper or cloth substrate. The goal is to create a thin, uniform layer that allows for efficient gas diffusion, electron transport, and proton conduction. Here you can see the structure. Air and water enter from the top, protons move through the membrane from the anode side, and the catalyst layer facilitates the reaction between oxygen and protons to form water. Different types of catalysts can be used depending on the application and performance requirements. Some common ones include platinum, platinum cobalt, platinum ruthenium, platinum nickel, and also non-precious metal catalysts, which are being explored for cost reduction. Let's now take a look at the different types of membrane electron assembly configurations used in fuel cells. Each configuration has its own structure and manufacturing approach depending on the application and performance requirements. On the left, we see the gas diffusion electrode or GDE configuration. In this setup, the catalyst layer is applied directly onto the gas diffusion layer and then it's hot pressed together with the proton exchange membrane. This method is commonly used for its simplicity and scalability. Next, we have the catalyst-coated membrane or CCM configuration. Here, the catalyst is applied directly onto the membrane itself. The membrane is then hot pressed with the gas diffusion layers, GDLs, on both sides. This configuration offers excellent control over catalyst loading and uniformity. The third configuration involves applying the catalyst layer onto an inert substrate. This layer is then transferred onto the membrane during the hot pressing process. This method is useful in certain specialized applications where precise control of the catalyst layer is needed. On the right side of the slide, we see a cross-sectional diagram of a complete MEA that includes internal gaskets for sealing, the gas diffusion electrodes, the catalyst layers, and the membrane. This layered structure is what enables the fuel cell to operate efficiently and reliably. Now that we have covered the key components of a fuel cell, like the membranes, the gas diffusion electrodes, catalyst layers, and MEA configurations, let's see how all of this influence the IV curve, also known as the polarization curve. This curve shows how the cell voltage changes with current density. Ideally, we want a flat line. That means constant voltage regardless of current. But in reality, we see a drop due to different types of losses. In the diagram of this slide, that is split it in 4 areas, we can see all the losses. Starting from the left of the diagram, which we have the activation losses, in the middle we have the ohmic losses, and in the right we have the concentration losses. Also, on the top we have the crossover losses. So, as we understand, every part of the MEA, from the membrane material, the catalyst structure, the GDE design, and the assembly method, directly impacts the shape and the efficiency of the curve. Our goal in R&D department is to flatten this curve as much as possible, minimizing the losses and maximizing the performance across all operating conditions. Now that we have explored the individual components, membranes, gas diffusion electrodes, catalyst layers, and the different MEA configurations, let's look at how they come together in a complete fuel cell stack. The core of our technology is the next generation high temperature PEM MEA with the ion pair membrane. As I have mentioned before, this membrane delivers 3 times the power density and 3 times the lifetime compared to traditional high temperature PEM systems. That's why our product has already been deployed in thousands of systems across the globe. Also, another key advantage of our system is the fuel flexibility. Thanks to the high temperature operation of our MEAs, we can integrate with methanol reformers and still use low temp PEM balance of plant components. Our stack design is also cost effective. Why? Because with a simple balance of plant, low maintenance requirements, and the ability to assemble locally in major markets, the cost reduction is huge. That brings us to the end of today's training. We have covered a lot, from the fundamentals of fuel cell operation to the intricate details of membrane and electrode manufacturing, catalyst layer design, MEA configurations, and how all of these components influence the performance of a fuel cell stack. We have also seen how ion pair technology and high temperature pair systems are pushing the boundaries of what's possible in clean energy. At Advent Technologies and through NICKEFFECT project, we are not just developing components. We are building the future of energy, and a future that's more efficient, more sustainable, and more adaptable to the world's growing power needs. I want to thank all our partners for their contributions and commitment to innovation, and of course thank you all for your attention and engagement throughout this season.